Welcome. In this video, we're going over the class discussion for Unit 2, Activity 2, Exponential Functions for Percent Change. So let's start with example 1, which is to decrease 200 by 10%. So we want to start with 200 and subtract whatever 10% of 200 is. And when you see percent, you should think this number divided by 100. So this is 200 minus 10 divided by 100 times 200. So this is 200 minus 0.1 times 200, which is 200 minus 20, which equals 180. Now, we can decrease 200 by 10%, or equivalently, you'll see that if you have 100 and subtract 10, it's the same as 90. We have 90% of 200 left over. So decrease 200 by 10% is the same as 90% of 200. Let's check our work and make sure that matches up. So I have 200 times 90 over 100, which is 200 times 0.9. And on your calculator, you notice that gives us 180 again. Let's look at example 3. Increase 480 by 35%. So we want to start with 480 and add whatever 35% of 480 is. This is equivalent to 480 plus 35, and again it's percent, so you divide that number by 100 times 480. So you have 480 plus 0.35 times 480. Now on your own calculator, multiply 0.35 times 480 to get 168. And you end up with 648. Now again, doing this same trick, except instead of decreasing, we're going to increase this time. So increase 480 by 35%. So we started with a whole 100% and added 35 to get 135. That's the same as 135% of 480. And now we can do this again. So 480 times 135% of 480. So that's 135 over 100 is 480 times 1.35. And you'll notice you'll get 648 on your calculator. Problems 2 and 4 are a warm-up to be completed after the video. At community colleges, students may enroll in one class, several, or enough to make a full-time schedule, also sometimes more than a full-time schedule. Because of the differences in the number of units students take, colleges calculate FTES, or full-time equivalent students. For the California community colleges, the number of FTES a college has determines how much funding the college receives from the state. Now, there are different ways to calculate this. CSUs and community colleges do it differently, but in both cases, this is an estimate of how many students would be attending the college if everyone enrolled full-time. So here we have some information from the 2005-2006 school year, academic year, for a particular community college. We're told they had 4,000 FTES, so full-time equivalent students, and they were prepared to increase the number of full-time equivalent students by 5% each year for the next few years. So part A, let's make a table to show the number of FTES for a 4-year period of time. And we need a little more space, so bear with me while I move some things around on my page. So that's better. I've moved some things around and I can see the important information. So we're starting with 4,000 full-time equivalent students and we're increasing 5% per year for the next few years. So of course, when 0 years have passed, we still have 4,000 full-time equivalent students. And here X is representing the number of years that have elapsed since this academic year. So for the next academic year, let's calculate this. And since these notes as they are written lack in space, I made a space. I would use scratch paper on your own if you're doing this. So for year 1, we have 4,000 times, and we want to increase by 5%, so we want to do 1.05. And now if you're having trouble seeing that, let me take it back a step. We're doing 4,000 plus 5% of 4,000. which is 4,000, plus 5 over 100 times 4,000. This is the same thing as 400 plus 0.05 times 400. And if you notice, we have a 400 in common on both of these, so I can factor that out to get 400. 1 plus 0.05, which is 4 times 1.05. So this is where the 1.05 came from. Now, what is this numerically? This becomes 4,200. Okay, so I'm going to write that here. And I'm leaving the colors just to show where each value came from. Let's look at 2 years since the 2005-2006 academic year, and I'll do that in blue. So when x equals 2, we have 4,000 times, let's start with the previous year, 4,200 times 1.05, and that gives us 4,410. But before I go on, I want to rewrite this. In fact, if you remember, 4,200 is the same thing as 4,000 times 1.05. That's 4,200 right here. But we still have this 1.05 multiplied at the end. And all of this equals 4,410. Now, where am I going with this? I have a 4,000 here, and I omitted a 0, so let me fix that. So again, we have 1.05 twice, so this is 1.05 squared. And all of this equals 4,410. So that's just another way to write this. And let's look at this pattern really quickly. 2 years after, we have a 2 in our exponent. 1 year after, we have a 1 in our exponent. So then let's take an educated guess. For x equals 3, we'd have 4,000 times 1.05 cubed. And that gets us 4,630.5. And I'm going to round up, so I'm going to round up. So this is about 4,631. Okay, so let's do this one final time. For x equals 4, and I'll do that over here. We have 4,000 times 1.05 to the 4th power, which is 4,862, and then after the decimals, 0.25. So that's about 4,862. Let's take a look at Part B. Part B, let's write an equation for the function and use that function to project FTES 10 years later. So we want something y equals AB to the x. And remember, A is the initial value. In this case, A equals 4,000, so this is the number of students or full-time equivalent students we started with. And B is the growth rate. So B, in this case, is 1.05, which we figured out on the previous page. So this is 4,000 times 1.05 to the x power. And we want to predict FTES 10 years later. So that happens when x equals 10. So y equals 4,000 times 1.05 to the 10th. And using your calculator, you should get 6,515. And after the decimal place, you'll get several things. 58 is what I'm rounding to. So let's round up to the nearest whole number, 6,516. So our prediction is that full-time equivalent students 10 years later will number about 6,516. Problem 3. Consider the functions h of x equals 28 times 1.27 to the x power and g of x here 28 times 0.93 to the x power. Which one models growth? Which function models decreasing quantity or decay situation? How do we know? Well, first off, let's see what they have in common. The 28 is in common in both of them, so that's not going to tell us anything. But we should know that already since this is our initial value is the 28. That's when x equals 0. Where they differ is here. Besides the name, H's and G's, that really doesn't matter. They differ in their growth rate. So h of x has a growth rate of 1.27, which is larger than 1. So this models growth. g of x has a, and I'm going to put this in quotes, growth rate of 0.93, which is less than 1. So this actually models decay. The key to remember is if the rate is larger than 1, you have growth. If the rate is smaller than 1, you have decay. Finally, for number 4, let's find an exponential function for the data in the table. And I am low on space, so I'm going to move this to another page. All right, for this final problem, we're going to find an exponential function for the data in this table. So let's recall what these functions look like. Typically, y equals ab to the x power. And we have some x's and we have some y's. In this case, we're not calling it y, we're calling it r of x. So r of x equals a times b to the x power. So let's pick an ordered pair. This one's 0, 500. What happens if we plug this in? R of 0 equals 500 times b to the 0 power, which is 500 times 1. And that gives us 500. Now let's see, was that helpful at all? Well, we have 500, b to the 0 power equals 500. Can I figure out a way to solve this for b? Well, dividing both sides by 500 gives me b to the 0 equals 1, or 1 equals 1. So this was not helpful. So in general, when you're trying to find equations for exponential functions, I would suggest picking an ordered pair that does not include a 0. So let's look at the next one. 1 comma 300, and I'm going to write this one a little differently. I'm going to write this as 300 equals 500 times b to the 1 power. Now why am I doing that? This here is r of 1. That's equal to 300. And this is a times b to the 1 power. Okay, now can this help me solve for b? Because that's my whole goal. I want to figure out what b is. So let's divide both sides by 500 to get 0.6 equals b. Look at that, I have my growth rate. Well, decay rate, it's less than 1. So let's quickly check that this is correct for, say, another one. How about we check for 3 here? So 108 equals 500 times b. And now I've been using the y value here, my initial value of 500 here, and then for the exponent, I've been using whatever the x value is. So if you notice, this was 0. This exponent here is 1. So in this case, we're going to use a 3 in our exponent. So 108 divided by 500 equals b cubed. Oh, now that's tricky. How do we undo a cube, I guess, on your calculator? Take a moment and see if you can figure that out. Now on your calculator, you don't really have a cube root function. So to undo a cube, you can write the 1/3 power. To undo b cubed, use b cubed to the 1/3 power to get b to the 1 power. So on your calculator, you want to do 108 divided by 500, and that'll get you 0.216 equals b cubed. And then you want to use a symbol that looks like this. And once you have that, you're going to type in 1 divided by 3. So this is 0.216 to the 1/3 power equals b. So b equals 0.6. We get the same answer again. That's wonderful. That tells me my equation is equal to y equals 500, my initial value, times 0.6 to the x power. Let's finish off with part B. When the growth factor is a decimal, we explain the changes of percent. What is a percent change per 1x value of the table above? So what we did on the previous page. And if you remember, we found y equals 500 times 0.6 to the x power to be our equation. And we know it's decay since everything is getting smaller in the table. Also, 0.6 is less than 1, so this is decay. Okay, so now what is the percent change? Well, let's look at the first couple values of the table. on your table in your notes, you should have this typed up. So I'm just resketching the first couple values. And we go from 500 to 300. So remember, our equation is 500 times b to the x, and our b is 0.6 to the x power. And here we have to use an exponent of 1. So this is 500 times 0.6. That should look like a percent change to you. In fact, 500 times 0.6 is the same thing as 60 divided by 100. So this is 60% of 500, which is the same as decreasing 500 by what? We can do 100 minus 60 gives us 40. So that's by 40%. And to check, look at this, 500 minus 40% of 500. So that's 500 minus 40 over 100 times 500, which is 500 minus 0.4 times 500. And you'll notice you'll get 500 minus 200, which is 300. And we have verified that these are equivalent now. So the percent change in this table is we're decreasing by 40%. I hope this video was helpful.